Welcome to another exciting and learning sessions of mathematics. I am Himani Asija, and today we shall learn about linear inequalities of class 11th. Let us see what we are going to deal with today. Linear inequalities in one variable, finding the algebraic solution of linear inequalities in one variable, representing this solution in the form of an interval and on the number line, rules of solving linear inequalities. Linear programming dates back to World War II between 1947 and 1949. The father of linear programming, George Dasning, designed various linear programming problems to maximize the profits and minimize the costs involved in real life situations. Linear inequalities and objective function are a part of linear programming, which is a part of mathematical programming. Objective function is being dealt in class 12, so we have linear inequalities in class 11. Let's consider a real life problem. If you go to the market with rupees 50 to buy some pens and pencils worth rupees 5 and 2 respectively, under a condition that you are buying 3 times the number of pencils as the number of pens. Let us buy x pens and 3x pencils. The amount spent on the pens would be 2x rupees. Amount spent on pencils would be 15x rupees. So, the total amount spent is given by 2x plus 15x, and since I have 50 rupees in hand, so the amount I spend should be less than or equal to 50. Therefore, 17x is less than or equal to 50, and the possible values of x therefore are 1 and 2. And the possible combinations of the pens and pencils are 1 pen and 3 pencils and 2 pens and 6 pencils. The values of x as 1 and 2 are called solutions of the given linear inequality. Let us have a glance on the previous levels. Consider a number line with integers marked on it. Consider the integer, say x equal to -2. Now, any integer on the left of -2 is less than -2 and an integer on the right of -2 is greater than -2. This is symbolically written as x less than -2 and x greater than -2 respectively. So, for x less than -2, the possible integral solutions are x equal to -3, -4, -5 and so on. And for x greater than -2, the possible solutions are x equal to -1, 0, 1, 2 and so on. Now, in this list, if we include -2 also, the first list looks like -2, -3, -4 and so on. The algebraic expression of the above would be written as x less than or equal to -2. Similarly, the second list will be written as -2, -1, 0, 1 and so on. The algebraic expression of the above would be written as x greater than or equal to -2. Let us represent this on the number line now. If we are to represent x less than -2 on the number line, let us draw a number line with integers marked on it. The integer -2 is being marked as the point A. Let us represent this inequality on the number line now. Consider the inequality x less than -2. Draw a number line with integers marked on it and plot the point A as -2. Since we are plotting the inequality as x less than -2, so we mark on the number line towards the left of -2. Since we have a strict inequality as x less than -2, we put a hollow circle at the point A, depicting that the point -2 is not included in my solution. In a similar manner, x less than or equal to -2 would be marked on the left of the number line and the point A here would be marked with a colored circle. The colored point A or the colored circle A depicts that the inequality is with equality, hence x less than or equal to -2. In a similar manner, the inequality x greater than minus 2 and x greater than or equal to minus 2 is marked. Since we are marking the inequality x greater than minus 2, we have a hollow circle at the point A and we mark the region on the number line which is on the right hand side of A. In a similar manner, x greater than or equal to minus 2 will have a colored circle at the point A and the inequality would be marked on the right hand side of the point A. We have represented an inequality on the number line. Let us see how intervals on a number line would be represented. A comma B with a rectangular bracket is read as a closed interval and includes the points A and B. Therefore, A and B are included in the list of solutions. For example, if we have 2 comma 5 in the closed bracket and we are dealing with integral solutions only, then 2, 3, 4 and 5 would be included in the answer. A comma B with a closed bracket at A and open bracket at B is called a semi-closed interval, and this depicts that the point A is included, but the point B is not. So, it will have all the integral values between A and B with A, but not B. A comma B with the closed bracket at B and open bracket at A is also a semi-closed interval and includes the point B, but not the point A. So, it will have all the values between A and B including B, but not A. With round brackets A comma B or open brackets A comma B is called an open interval. This includes all the points between A and B, but not the points A and B. So, 2 comma 5 with an open bracket or a round bracket would include the integers 3 and 4, but not 2 and 5. Minus infinity to A is an open interval again with an open bracket at A and open bracket at minus infinity. Note here that minus infinity or plus infinity, wherever taken, will always have an open bracket and never a closed bracket, as one can never reach minus infinity or plus infinity. So, minus infinity A is an open interval depicted as all the values which are less than A. A comma infinity with an open bracket depicts an open interval again with all the values which are more than A. In a similar manner, minus infinity A now has a closed bracket at A and an open bracket at minus infinity, is a semi-closed interval and is depicted as all the values x which are less than or equal to A. Note again, minus infinity cannot be included in the interval, but A here is included. Similarly, closed bracket at A and open bracket at infinity is a semi-closed interval and depicts all the numbers x greater than or equal to A. Let us take up some examples. Find the integers in the interval 2 comma 8 with closed brackets. The integers are 2, 3, 4, 5, 6, 7 and 8. Integers in the interval closed bracket 2 open bracket 8 are 2, 3, 4, 5, 6 and 7. Similarly, integers in the interval 2 comma 8 open bracket 2 and close bracket at 8 are 3, 4, 5, 6, 7 and 8. Integers in the open interval 2 comma 8 are 3, 4, 5, 6 and 7. Now, let us solve the inequality minus 2 less than x less than 5 graphically. This inequality would mean minus 2 is less than x and x is greater than 5. Since we are dealing with these two inequalities together, we will take the common solution of the two inequalities. Let us plot them on the number line and select the common solution as the answer. We have already talked about the plotting of the inequality x greater than minus 2 and the plotting of inequality x less than 5. Let's plot these two inequalities separately on the number line. For x greater than minus 2, the graph of the inequality would look like this, and for x less than 5, the graph of the inequality on the number line would look like this. Now, since we have to look for a common solution for minus 2 less than x less than 5, we have to find the region which is common to both the figures. The region common to both the figures would lie between minus 2 and 5 and would look like this. Let's summarize what we have learned today. The importance of linear inequations in one variable in real life problems, solution of a linear inequality in one variable, representation of solution of linear inequality on the number line, types of intervals, and finding common solutions to given set of linear inequalities. We will meet you in the next episode with more real life problems in linear equations in one variable, the rules to solve the linear inequalities, real life applications of linear inequalities in two variables, and solving these linear inequalities in two variables graphically. So, till then, goodbye.